Welcome to Horsepill, a new type of Linux rootkit in South Seas CDF with Michael Leibowitz. Before we begin, a few brief notes. Stop by the business hall located on Bayside AB. The Black Hat Arsenal is on the Palm Foyer on level 3, and of course the Arsenal reception at 1700 hours. If you haven't picked up your merchandise, today is your last chance to visit the Black Hat Swag and Bookstore. Visit the Kali Linux Lab in Mandalay Bay A. And thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick it up. And with that, we welcome our speaker.
Hello, I'm pleased to be presenting my first time at Black Hat, and this is Horsepill, a new kind of Linux rootkit, as she said. And I'm very excited to be speaking at Black Hat because, as the name might suggest, this is a reference to Joanna Rutkowska's blue pill that she presented here, and this is a little more coarse than blue pill, which was somewhat elegant. So it's kind of coarse. It's like a horse pill. And also, this is an idea that we have a group in Portland called DC 503, and it's like Hacker Fight Club, and you show up, and you get to, it's like if it's your first time, you have to talk, and every time you have to talk. And I showed up, and one time I didn't plan ahead, and I had to talk, and this guy went, and that guy went, and that guy went, and I thought, crap, I really need to come up with an idea. And this is the idea I came up with while I was waiting for them to give their talk, and trying POC really fast. And so if you don't have a local hacker group you go to, you should go to one. Or if you don't go to a local hacker group, you should go to one. So I'm Michael Leibowitz, also known as Rootkit. I work for Intel. I'm part of the Intel Red team. I'm also a NSA Playsite contributor, where we have fun with re-implementing the leaked Ant catalog, and I've done a bunch of different things. I've done application development and embedded stuff and security stuff, and back to security stuff, and back to development, and back to security stuff, and back to security stuff. So basically what we're going to cover, what a rootkit is, how rootkits have worked in the past, go into how your computer really boots, what a container is, and then stringing it all together into making a rootkit, a demo, a little bit of a discussion about what this rootkit gives you, what sort of properties it has, and then finally detection and mitigation. So what is a rootkit really? Because this term kind of means different things to different people. And so to me, a rootkit is a post-exploitation tool. So this is not something that's going to get you that privilege, right? This is something that after you've exploited the box that lets you maintain that access that you have. So the essential characteristics here, of course, that it's persistent. In other words, it's difficult to remove. And it's covert, that it's difficult to detect. And so one way you can think about this is post-exploitation from a software exploitation perspective. And then one way you can think about this is another sort of physical exploitation. So if you think about the evil maid type attack where you leave your laptop unattended and classically, I guess, in a hotel room, and then the evil maid comes in, and then the evil maid rewrites your bootloader, and then you've been exploited, right? So this is a similar post-exploitation. So this is something that the evil maid can apply. So let's go through some sort of historical rootkits. And so the oldest kind of rootkit that I could, oldest kind of Linux rootkit that Linux or Unix rootkit that I could come up with was hard to call a rootkit exactly, but basically it's a series of backdoored commands. So the attacker would break in, and then they would backdoor inetd. And for those who don't quite remember what inetd, a long time ago in a galaxy far, far away, you didn't have a whole lot of memory, so you would write internet daemons that just talked on standard in and standard out, and then inetd would accept the socket connection for you and then would run this program. And so they would just backdoor inetd, so instead of running just your programs, it would also run a backdoor shell. And then you would be able to see that backdoor shell, so that's bad. So then they would backdoor all of the different little tools that the sysadmin might use to see that backdoor shell. So you would, backdoor PS so that it doesn't, it can't see the backdoor shell, and you would backdoor sum so that all the backdoor binaries look right, and top so you can't see the process, and find so you can't find the hidden storage, and also find can look at attributes, and LOSF so you can't see the processes when you look for who has sockets, and netstat so you can't see the port open. And then you have a shell you can access over the internet, then everything is good. But this isn't really used much anymore because firstly, most people don't run inetd, and secondly, it leaves a lot of forensic garbage on your disk, and thirdly, you can't exactly catch them all, right? There's going to be some administrative tool that's going to expose this hidden process and hidden connection, hidden storage. So, the world moved on to LD preload-based rootkits, and there are a number of these that have been talked about recently, like Jinx and Jinx 2, and then there's a few others, and there's actually a related one that I have forgotten the name of, where they backdoor a RAM disk with an LD preload rootkit. But basically, so if you're not exactly familiar with how dynamic linking works, there's your program, and then there's dynamic libraries, and the dynamic libraries are loaded, and there is an order of precedence. And typically, dynamic library symbols are weak, so that a symbol before that library clobbers the ones later. And also, fortunately, in libc, basically all syscalls are wrapped in a library function. So by LD preloading, you can basically change what the syscalls do by hijacking the syscalls. And this is typically cleared on setuid, because if you could LD preload a setuid binary and then run it, that would be bad. But there's actually a special file called ld.so.preload, and everything that has a list of LD preloaded libraries, and every dynamic binary on the system, regardless of whether it's setuid or not, will have this library preloaded. So you just make a you make a dynamic library that clobbers stat and opendir and readlink and readdir. And with the way in which these are used, you basically blind the system administrator from being able to see any of the malicious content, processes, connections, etc. So if it keeps you from being able to. The reason that it's opendir and readdir and these things is, and I'll go into that a little bit later, is that when you run PS, it's actually going through the proc directory and looking at all of the processes. And then when you go through, and when you're looking netstat, it's actually kind of doing the same thing. So by cleverly detecting what is being statted or what is being opendir'd, you just have it skip your process when it iterates through proc. And you just have it skip that line in the TCP listing where your shell is. And when you try to stat one of the backdoor files, it just doesn't exist. But the world kind of has moved on from that too, because firstly, there's a considerable amount of leakage with this. Yes, you can wrap the syscalls and you can be pretty clever, but there's a noticeable footprint that is kind of observable of the backdoor processes. And also, although your system is almost entirely dynamically linked programs. It actually probably has a few statically linked programs. And statically linked programs don't see these, they're not blinded by this LD preload type rootkit. And so once you do that, then it's trivially detectable. So, then there's, how about just a malicious kernel module? Ring 0 is all powerful, right? And so, and this is like basically rootkit, Linux rootkit, like how-to, right? There's actually books you can buy on how to write a rootkit, how to write a Linux rootkit, and it walks you through making malicious kernel modules. Because it's actually a pretty good vector. You can make invisible network connections, files, processes, the module itself. I mean, basically, it's kind of tricky, but you can manipulate the list so they basically just, as you iterate the list from user space, they just step around your module. And there's all sorts of other evil you could do as ring 0. You want to you want to write into places that ring 3 can't write in. You can do that. You want to steal things out of the kernel crypto keyring. You can do that. And it works. But this is also something that we have a way to mitigate, because basically kernel module signing is a thing, and it's fairly widely deployed now. If you have a Red Hat-based system, basically all the modules are signed, and whenever you load a unsigned module, it will still let you load one, but it taints the kernel. And so detecting that you have a malicious kernel module when your kernel is tainted and you don't think it should be, then becomes fairly straightforward. And it's quite likely on the horizon that that will be an enforced signing, where you simply cannot run any kind of kernel module that isn't signed. But kernel modules touch disk, and everyone wants to have super elite covert diskless malware, right? So you can actually just splat your rootkit directly into devmem. It's kind of a corollary of the module rootkit, except in this sense where you have the hooks when you load a module to kick off your invocation, and you have linkage to actually find those symbols. Now you're on your own to find those symbols and trigger those executions. So it's a game of exploitation, but you certainly have an advantage in that you can read and write all memory. And it's basically the same, right? You have malicious network connections, and you can hide anything from user space behind the veil of kernel space. But you don't really see this very much in the wild, because why? Because we no longer have devmem as really permissive to where root can just scribble all over kernel memory. That would be silly. So let's talk about containers, because this is a container-based rootkit. So what is a container really? I think container, likewise to rootkit, means a lot of things to a lot of people. And so in this instance, what I mean by container is basically a namespace and C group based container. So this is what, when you run Docker and LXC and OpenVZ and a few other things, this is the sort of containerizing system that they are doing. And basically what namespaces do is it says, okay, well, what we're going to do is we're going to divide up the kernel subsystems into these 6 distinct areas, and then we'll make namespaces of them. And so you can create a namespace, and if you create all 6 namespaces together, then you have what looks like a Linux system in microcosm. You have there's a IPC namespace for System 5 IPC objects. There's a mount namespace, so your little container can mount and unmount things, and it doesn't affect the host system. And there's a net namespace. You can make network adapters and add routes, and it doesn't screw up the host system. And a PID namespace, so you can make processes. Obviously, don't affect the host system. And a user namespace so you can have different users, and then a UTS namespace. And a UTS is like for setting the system time and host name. And I said namespaces, and I think that we sometimes think about namespaces as all like on the same level, right? It's just a separate set of buckets. But some of these are hierarchical and some of them are not. And so like things like PID namespaces, well, that's kind of hierarchical because PIDs are hierarchical. And but things like hostname are not really hierarchical because you couldn't really construct a logical hierarchy of hostnames now, could you? So, and then there's C groups. So C groups, what C groups let you do is C groups let you place processes in groups. And so it lets you make, for example, a set of resource limits that all these processes in this group are subject to, or a set of devices that this group can't touch, or things like that. And this is basically how container systems work, right? They make all the hierarchies, and then it looks like you have a little Linux microcosm, and they keep you from eating the system by placing you in with C group resource limits. So how do we manipulate at a programmatic level these namespaces? So basically, there are two syscalls. There's unshare, which effectively creates a new namespace for this current process, and then there's clone. And most Unix programmers are familiar with fork, and clone is the sort of Linux underpinning of fork, although fork is also its own syscall. So clone is the magical mystery Swiss Army knife of process creation, right? Clone can make you threads, clone can make you new processes, and in this case you just pass flags in there to make clone make a new namespace for this new process you are making. And then on the bottom here you see a list of namespaces. So from user space you can actually see these namespaces. They're exposed in the proc PID entry as the NS directory, and it's a series of symlinks to inodes, essentially, special kind of inodes. And you can actually traverse these namespaces. So if you had a process and you wanted to, this is how LXC enter works, like if you wanted to go into that container, you can call setNS and then use that inode of that namespace, and you can enter that namespace. And fortunately, for reasons you'll see later, the namespaces are not random. Like these inode numbers are deterministic. So they're defined in the Linux proc NS file, and you can see like basically it kind of looks like some random jibber jabber number, but actually they're deterministic. Okay, so let's talk about PID namespaces. So this is basically it's somewhat contrived, but this is a process graph. So processes are a hierarchy, right? There's a fork, or there's a top process called init, or if you're a systemd person, PID-ines, and it calls fork, and then it has children, and they can call fork, and so on and so forth. And so everything looks all normal except for to the left of PID-10, right? Everything on the left side of PID-10 is normal, and then when PID-8 forked PID-9, and then on the next call to clone, it passed in the clone new PID flag, and it made a new PID namespace. And so from PID-8, or from everyone to the left of PID-10, PID-10 looks like PID-10. You do a process listing, you see PID-10, and all of its children, PID-11, PID-12, PID-13. But then if you are PID-10, it sees itself as PID-1, as a init. And all of its children similarly, because it is in the new namespace. So it is the init of the container we've made, but we've made it only for PID namespaces. And init has like some special properties. So basically, a daemon is a process that forks and kills their parent, and then they become reparented to init. And init has some special properties as well. So of course it is the parent. It can reparent all the processes that kill their parents. Processes are mean. And also it can if it dies, the system panics. Like if you've ever had your system say like, and it tried to die, or and it killed itself or something, then the kernel panics and you're done. And then it handles like some convenient things, like when you hit Control-Alt-Delete, rebooting the machine and stuff like that. So, how does your computer boot? Well, basically, you know that your stuff starts after systemd, and then there's like some other stuff before that. And let's go through like how that really works from UEFI through systemd and all the way to your stuff. So if you've booted a computer post, or I should say with a Windows 8 sticker on it, that means basically that it's a UEFI secure boot platform. And so we'll do this in sort of picture form. And I think that this is kind of the classic UEFI secure boot kind of picture, although maybe a only slightly different. But basically, the UEFI runtime verifies the shim, which the shim is what your distro provides, and it has a stored signature database in it, the DB list, and the DB list has the Microsoft third-party signing cert in it, which verifies the shim that has been signed by Microsoft, and it will boot the shim. And then the shim has the distro certificate, signing certificate in it, Red Hat or Ubuntu's or whatever flavor of Linux you have. And then it will in turn boot Gummy Boot or Grub and verify it against the vendor cert that's inside the shim. And then Gummy Boot or Grub will in turn boot Linux and verify it against the same cert, at least in modern times. Apparently in Ubuntu 14.04, Secure Boot was a compatibility feature only, and Gummy Boot Grub did not actually enforce the signature of the kernel. But don't worry, that's not a security bug because it's not a security feature. But, Linux isn't really what you're interested in on your computer. You're interested in your stuff. So how does your stuff get booted? Well, so Linux actually, on almost all Linux distributions, boots a RAM, loads a RAM disk, and that RAM disk then in turn execs systemd, your init system, and then eventually it gets to your stuff. And these are sort of maybe color coded in terms of in terms of like what's protected and what's not protected. So, okay, your bootloader, that's protected. That's like protected by UEFI. And your kernel, like, okay, that's transitively protected by UEFI. And the modules, we know how to protect modules. We can sign those with a ephemeral module signing key. And the rootfs, I put a check there because, there are well-established ways to protect the rootfs from tampering, right? We have Verity and IMA, and there's some even older things like that. But like, basically, as an example, if you have an Android phone, the Android root is verified, the Android system partition is verified with Verity, and that's what protects it. But the initRD, there really isn't a very practical, widely deployed way for normal Linux systems to protect that. Short of like bundling it into the boot blob, which is kind of what Android phones typically do, or just not having one, there isn't really a good way to protect it from modification. And in fact, that's kind of like by design because the system modifies its own RAM disk. So what's in a RAM disk? So basically, we have like, a RAM disk is about, 30, 40 megs on, compressed, and it's got like all the kernel modules in it. And it's got like a set of like minimal user space kind of utilities, and it's got some init scripts that do, the stuff you want. And, you can see that the kernel modules are in there. And so what happens is every time you update your kernel, or any of those minimal utilities are updated on your system, and you think about it, your kernel kind of updates at a fairly reasonable frequency, at least I hope it does, then the RAM disk is reassembled so that those modules are put into the RAM disk. And we'll talk about that a little bit later too. So, what is your RAM disk supposed to do? Well, your RAM disk loads all the modules you need to run your hardware, basically, at least at boot time. Responds to the hot plug events as your hardware enumerates and loads the appropriate module. If you use Lux or DM crypt, right? It runs crypt setup, gets your crypt password, and then puts that into the device mapper, and then it finds them out to rootfs. And actually, now the RAM disk that's been uncompressed into memory is like 60 megabytes in size, and this memory doesn't exactly go away. So then what it actually does is it deletes everything inside the RAM disk, and then it doesn't exactly pivot root over. It moves the root mount over the RAM disk, and then ta-da, execs in it, and your system is up. Okay, well, we just modified your RAM disk a little bit, and we kind of inserted a backdoor. Okay, so, what does your RAM disk do now? Well, it's kind of similar, at least at first. It loads the modules and hot plug events. That's good. It still does that. And it does crypt setup. That's good, and does that. And it enumerates the kernel threads, which I'll talk about in a moment. But okay, that's a little new. And then it calls clone, and it calls it with the clone new PID and new NS, which is a new mount namespace. And then it makes child process, and that just remounts proc, because proc shows the namespace shows the perspective of the namespace for which it was mounted in. And so we want proc to have the child namespace view so that PIB1 thinks it really is PIB1. Then we'll make some fake kernel threads to make it look legit. Clean up initRD and exec init. Okay, this doesn't seem so awful. Then we'll remount root, because root is usually read-only at this stage, and we'll just remount it read-write for our purposes, because we probably want to write to the root partition. We'll make a little scratch space that we can use that doesn't touch disk, so that we can store whatever cool goodies we have. And then we'll just make some extra little helper processes, like a backdoor shell and something to keep our persistence. And then we just wait to see if anything dies, because remember, init has to harvest all of the children who've demonized. Otherwise, you get zombie processes. Have you ever seen zombie processes and you have a bajillion zombie processes? That's because the parent is not waiting for the child process's exit status. And then if the child init wants to reboot, then we'll reboot, because that's what we do. So when the child, in the child namespace, when you call shutdown, or when you call reboot is actually the syscall, it actually sends a signal to the parent of the child of the child that's outside of the namespace, and says like, hey, they want to turn off the computer. What do you want to do? And since we don't want to look like the system is completely owned, we'll just turn off the computer like they ask. So what about these kernel threads? What is that about? So if you've ever run PS and you see like all this garbage that you basically ignore, these are the kernel threads. And there's really only one scheduler, and it would be a real pain in the butt to have like two schedulers, one for kernel tasks and one for user space tasks. So basically they're all scheduled together. The kernel tasks are obviously more important than your tasks, and they get scheduled first if they want to. And this has all the different kernel threads that you have, which you have a lot. And this also lets you, they also have the same scheduler accounting. So this means that you can see in user space, like if RCU locks are taking up a lot of your time, you can actually see that in the user space view of the process list. But when you make a PID namespace, there's no kernel threads there. So if you logged into a system and there were no kernel threads, like that would, and you thought there should be, that would be suspicious. But the good news is, you can make fake processes that look just like them. So the effort to bring containers to Linux also brought the desire to have migration of containers. And migration of containers works through something called CRU, Checkpoint Restore in User Space. Originally, this was tried as a kernel space mechanism, and the kernel community said, no, let's do this in user space and provide the necessary hooks to do this. So basically, you can pickle any Linux process, put it into a file, and then take it somewhere else and reanimate it. It's pretty awesome. And this includes its memory map. And so Linux introduced a helpful PRCTL that lets you set the map and get the map. And this is interesting to us because the arguments, what you see in PS, and which is actually what's in procpid status and what's in procpid command line, you can effectively change by saying okay, here's a new argv that I want to be my argv now. And you just call PRCTL mmap, and there you go. And then there's another syscall or another PRCTL to set the process name. And between those two, if you do those two things, then it will look right in PS, and then top actually looks at processes slightly differently, and it will look right in top. And so it's reasonably convincing. So okay, let's go through. We've talked about process invisibility, and we've talked about storage invisibility. I kind of alluded to storage invisibility, but because we unshared the mount namespace, you can mount a RAM disk there, and the child namespace can't see it because you're in a different mount namespace. And now you have a convenient place to stash things in volatile memory, and when the computer's rebooted, there's no forensic trace of it. But what about network invisibility? That's pretty important, that we have a backdoor shell that you can't detect. So, you want the system, and when they run netstat, not to see some port they're listening and some shell sitting there. And so how does netstat work? So the way netstat works is actually it goes through two files actually, but I'm using TCP here, procnet TCP, and it has a line. It has a line for every socket connection. And it has a bunch of different columns, but the columns we're interested in, there's a local address, a remote address, and an inode. And so the addresses are in hex. So obviously the remote address is 0. It's listening to everywhere. 35 is 53 in hex, so this is TCP DNS. And the internet addresses are backwards because it's network rules, not host rules if you're on a little endian system. So that's 7F is 127, so that's 127.0.1.1. That is that's a local that's DNS mask, or that's DNS mask essentially, a local caching DNS server. And then when you want to see okay, what process has that open, you iterate through proc and you look in procpid FD, and then you look for that inode number in the in each process. And so the point of this is even if you can't see the process, you can still see that the port is open. Because procnet TCP will show you the port is open, and then netstat, when you ask what process has this open, it will just kind of say I don't know. It'll put a dash there. I don't know what process has this open. So that's no good. We can't just have a TCP connection open that the system can see. That would be bad. Oh, I was supposed to talk about something else there too. Okay, so right, we can't have a TCP port listening because that would be bad and it would be trivially detectable. So there is a way though that we can make sort of an ephemeral connection that provides the sort of connectivity that's also appropriately sneaky. So we can make a DNS tunnel, and so DNS tunnels are great because usually DNS will resolve, right? Even if you're in some horrible DMZ deep in a bunker, generally DNS resolves, right? And so, and DNS is a hierarchical system. So you You do your DNS query, and if the upstream server doesn't know, and it goes up to the root, and then eventually it goes down to the DNS to the actual owner of the domain that has the name server, and then it replies. And so, hey, you've got communication here. And so a DNS tunnel just makes queries that actually relay data. And so we're using Rombo's DNS cat 2 to set up this DNS tunnel for us. And it works. Okay, but how do we make it persist? We know we can backdoor the RAM disk, and we can have our processes there and our storage there and our connection there. But what happens when they want to update? Then we're screwed, right? Well, remember how I said the RAM disks were assembled on the system? So what happens is the RAM disks are actually gzipped CPIO archives. So what happens is you install your kernel and modules and whatever, and then it calls a hook that updates. And in the Ubuntu and Debian world, it's called update init ramfs, and in the Red Hat world, it's called Drakit. Or anyway. So what it does is it assembles it into, it makes a temperature, and it sprays all these files in there of what the RAM disk is supposed to contain, and then it calls CPIO and archives them up. And we just have a process that just hangs out and waits for those to be created, and as soon as the binary that we backdoor is called runinit, as soon as the copying finishes writing runinit, we just write our own. And then when CPIO is called to archive it all up, it archives up our copy. This is great. There's sort of a race here, but the good news is we're in a position ahead of you in the race. So we'll just set our scheduling class to real time and your scheduling class not to real time, and we'll win the race every time. And then it leaves very little sort of forensic trace, right? The only extra step here is a rename, a write and a rename in the assembly of the of the RAM disk, which is hundreds of files are splatted in there. And it happens with some degree of frequency. So basically, if you're monitoring the system, basically this is noise. You never look, init ramfs was called, and it splatted all these files, and that's normal. Oh, okay, it's the demo time. Excitement. Okay, so then we get to. Then let's see how good I am with the xrandr command line. Oh no. Technical difficulties. Where'd the display thing go? Oh. Yeah, this looks good. You guys can see this, right? Okay, cool. I gotta get my notes because it's kind of a long demo script, and I can't read my notes anyway. Okay, YOLO. Okay, so can you guys see and or read this? Not that. This. I'm going to assume that's a yes. Okay, so what do we have over here on the right? Over here, I don't know if you can see my mouse pointer or not. We have our command and control system, and over here on the left we have our victim, and this is the victim VM. So let's just land on the victim. That was easy. And so let's see, we have our runinit binary, and what I want to show you about the runinit binary is that we have a special section since, like, not everyone has the, oops, I typo. Everyone has the same CNC system. So you need to be able to set that. And so we have this like DNS command line, or this DNS command line section in the binary, and you can see that it's like fail, fail, fail. So we need to make a secret. That should do. And then we need to set that into our binary. And then we just are basically setting the DNSCat command line options that it will run. And we got to put in our host name, our domain name, and that's like kind of a hard one to always type correctly each time. If you don't type it correctly, it doesn't work. And then we have like a cool little logo, and that looks right. And then if we run objdump again, you should see that, yay, our secret is in there. So great, let's exfil it into the victim. Or is that's probably not exfil if you take it from your system and like put it into the victim. Anyway. Okay, and then we'll just, we're being tricky, so we'll just base64 encrypt it. And then let's send it to pastebin. This is fine. Chug, 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 chug. Cool, and we get a URL. That's neat. So now let's, we need to exploit the system so that we're root. Fortunately, the system came with one. Awesome. So now let's do some little trickery. Let's unshare the mount namespace so that we can scribble all over into a space that no other process can see. And we'll just like pop a RAM disk over lost and found to do our evil work. This is good. And then we'll just get it back from termbin, rbkc. Remember to base64 decrypt it. And if this works correctly, yay, we have binaries. So now we'll just horsepill install running it, and it will do that. And then we'll go to our server, and it's hard to talk and type at the same time. We'll just use that key we made before, and then we'll spell it hopefully the same way, and then we're running that. So now we'll just, we've infected it. Well, let's reboot, and then this is our system here. So we're rebooting. Doop doop doo. There's good old Tiana core, and then let's make this slightly more verbose so that you can, so it doesn't just show a black screen because that's boring. And I have to wait for it to boot before we can get back in. Uh-oh, I'm running out of time. This is the race. Can I pull off the demo before they throw me off stage? Okay, Linux is booting. Oh no, we've been pwned by Horsepill. And then we, you know, it's a pretty good logo, so we leave it on screen for a while so that you can see that you've been owned by Horsepill. Also, it's locks are silly. You can just sleep out the race. So our system is back up, and everything kind of looks normal. You can see there's no weird stuff running. The kernel threads are all there, and it just looks normal, and you don't see anything really weird. And then, all right, and then we have our backdoor shell. And DNSCat works a lot like Meterpreter, except for slightly more flaky. Oh, wait, I have to tell it to spawn the shell. Then I have a new window. And, okay, and now here I am. I'm root. We can exfil the shadow file and do other sorts of nastiness and etc. But let's see if I can blow through the rest of the slides really fast. Not that one. Oh no, pre-rendering. Crap. Hurry up. This is what I get for not bringing a fast computer. Oh, you're seeing my weird presenter view, aren't you? Yeah. Okay, so we've shown that it's, we'll blow through that. We showed that it was persistent and all that. So let's talk about detection. So as I said before, you have these deterministic enumerators of the namespaces. So actually you can look in procpid.ns and just see that you're not the namespace you think you should be. That means you're owned. And these kernel threads they kind of look like kernel threads, but they're not real kernel threads. So real kernel threads, their PPID is 0, and these kernel threads, their PPID is 1, so that's kind of a little fishy. And there's only one audit subsystem on the whole machine. So even though you're playing all these silly these silly namespace games, actually, audit actually sees everything you're doing. And obviously you can take apart the RAM disk and you can see that a 4K binary became a 180K binary, and take it apart and see that there's nasty crap inside. So, but what can we do to make this not happen? So basically, after going back and forth a lot on this, we just need to stop assembling RAM disks on kernels. We need to rely on the same semantics of secure boot, and if you think about the way secure boot works, basically you can think of it as there's a secret that you don't know. And the problem with the assembling it on the system is you can't keep a secret from yourself. And we don't ship 1,000,000 kernels for systems. We make a generic kernel that works for just about everybody. And then likewise, we can make a generic RAM disk that works for just about everybody. And we could actually cryptographically verify that RAM disk. And that would actually completely eliminate this threat, and it would completely eliminate all the ancillary threats related to it, backdooring, backdooring the crypt setup so that it exfiltrates your crypt LUX key as you boot, and all those other sort of funny games that have been presented before. I only have 1 minute left, so you can draw your own conclusion. And and there's no Q&A time, but we're going to do at DEF CON we have the DC 503 Lounge from, I think, on Saturday from 1 to 3, and all the DC 503 presenters will be in there, and you can talk to us and ask us questions and tell us that we're terrible people, etc. Thank you very much.